matrix is called non-normal if it does not commute with its Hermitian adjoint. And since we will be discussing mainly random, only I would say random non-self-adjoint or non-Hermitian matrices, such matrices, when they when they are non-normal, they have usually with probability 1, they have a set of n distinct eigenvalues. So z1, z2 to zn. They may be both either complex or sometimes they can be real. We will see such instances. And to each eigenvalue of the I of such a matrix, real or complex, corresponds to eigenvectors. This is in contrast to self-adjoint matrices when we have only one set of eigenvectors. And for non-normal matrices, we have left eigenvectors and a set of right eigenvectors, and the corresponding eigenproblems written here. So right eigenvectors are just when we multiply x from the right with a vector, we get zi ri, and when we multiply it with left, we get the same eigenvalue, but for a different, in general, for a different eigenvector L left. Or if you like, left eigenvectors are right eigenvectors of a joint matrix. It's easy to see, corresponding to this eigenvalue. Now, it's very easy in a standard way, textbook way, to show that the set of left and right eigenvectors satisfies the property which is called biorthogonality. Namely, let us take these two eigenproblem equations and multiply the first one with the left with, say, Lm, and if say for a given value of the index k, and multiply the second equation for the left eigenvector with the right with rk, and then we see immediately that if eigen values zk and zm are non-equivalent, as we agreed already for random matrices, this always will be the case. It's only, we immediately see that left and right eigenvectors corresponding to different eigenvalues, they are orthogonal, and we always can impose normalization condition so that we will call it biorthonormality. This condition is precisely written here. And the first immediate consequence of this normalization, of the chosen normalization to 1, is that by Cauchy-Schwarz inequality, the following combination, just a scalar product of left, one can say scalar square of left with itself and right with itself, and this product, square root, will be always larger or equal than 1. And we will see that this right-hand side, the square root, will play an important role. And to elucidate this role, let us discuss simple problem of characterizing stability of eigenvalues of matrices under additive perturbation. What I mean by this, let us consider now, starting with the non-normal matrix S, let us additively perturb it, just add to it a perturbation of the form epsilon times p, where epsilon, we can consider it in fact real, positive, is a parameter which controls magnitude of this perturbation, and the norm of a matrix P, say 2 norm, is fixed. Then for this perturbed matrix, which we denote as x epsilon, with subindex epsilon, we can write corresponding right eigenproblem in the standard way. And now basically multiplying it from the left with left eigenvector of unperturbed matrix of X, we can easily derive the identity that difference between eigenvalue Zi at some value of parameter epsilon and Zi at value equals 0 is just equal to epsilon times the ratio of perturbation P sandwiched between unperturbed or left eigenvector of X of unperturbed matrix times P times from the right eigenvector of perturbed matrix and divided by scalar product of left unperturbed and right perturbed. And then if we consider, as we should, this parameter epsilon small, then in the leading order in epsilon, we just in this ratio should, in order to keep the leading order, should put epsilon equal to 0. So we immediately see that using Bayer normality, that modulus of this difference between perturbed and unperturbed eigenvalue is basically equal to perturbation sandwiched between left and right eigenvalues corresponding to the eigenvectors corresponding to the eigenvalue that we perturb. And again, using Cauchy-Schwarz inequality, we see exactly that this magnitude of this change in or difference between perturbed and unperturbed eigenvalue will be always smaller than to the leading order epsilon, the norm of this perturbation, which is considered to be fixed. And then this combination that we already seen, the square root of product of two scalar products, or of norms of right and left eigenvectors corresponding to this eigenvalue under consideration. And we immediately see that basically this parameter, this square root, exactly controls the sensitivity of eigenvalues of non-normal matrices to perturbation. And since it's larger or equal than 1, as we already discussed, we see that non-normal matrices are more sensitive to perturbation than their normal counterparts. And this parameter, which is known in the literature as eigenvalue condition number, it's can be only 1 for normal matrices. So it's a useful quantity which in some sense characterizes or can be used to characterize non-normality, one of quantities which is conveniently characterizes non-normality of the matrix. So dealing with random matrices, it's natural to ask how well conditions or sensitive to perturbations are eigenvalues of a typical in the sense of taken randomly according to some specified probability measure or ensemble. The simplest or the standard choice of random matrix ensembles, as probably many or all of you know, is to take entries of the matrices Gaussian distributed. So for this case of matrices without self-adjoint constraints, so just generic non-self-adjoint random matrix, natural ensemble is just to take, if we consider matrices with real entries, just to take all these entries to be normal variables with mean 0 and variance 1, and such ensemble is called real Geneva ensemble. Or one can consider, and in fact, in most detail, technically, in most cases in these sets of 3 lectures, we will concentrate on the complex counterpart of this ensemble, when every entry is independent and identically distributed variable, and also real and imaginary part of every entry is a normal variable. It's conventional to take mean 0 and variance 1/2 for them. Now, what one can say about eigenvalues of such matrices? If one starts with real Geneva ensemble, then since all entries are real, characteristic polynomial obviously will be polynomial with real coefficients. So eigenvalues, which are roots of this polynomial, can be either real or come in complex conjugate pairs. And it turns out...
Jan, sorry to interrupt you. We do not see your pointer, your hand, if you want to show something. Now
okay. Thank you for pointing this. Okay, so basically, here on this view graph, I just showed the picture which is obtained by simulating many instances of real Geneva ensemble. I think of size 100 by 100. Eventually, we always will be interested in understanding properties for large values of n, but we will derive many expressions for in fact given n, but eventually we will be interested in large values of n. So with growing n, as this picture shows, eigenvalues tend to concentrate in a circle of radius square root of n, and majority of eigenvalues for such real Geneva matrices of order of n will be complex in the complex plane uniformly for large n, filling in interior of a circle of radius square root of n, but there will be of order of square root of n real eigenvalues which accumulate on the real axis, and of course it's subleading order, but they may also show some interesting properties. So in principle, when dealing with real Geneva ensemble, one should separately ask about properties of real eigenvalues and those positioned somewhere in the complex plane. But this feature does not exist for complex Geneva ensemble. For complex Geneva ensemble, all eigenvalues are complex with probability 1, and they for large n uniformly fill in the interior of a circle of radius square root of n. Now, as I mentioned, we mainly concentrate in these lectures on complex with writing the joint probability density of all its entries. A complex Geneva ensemble I will denote by capital G, and joint probability density with respect to flat Lebesgue measure is just given by exponential minus trace of Geneva matrix times its conjugate. So from this form, it's obvious that entries are Gaussian distributed complex numbers, and just restoring normalization, we get this normalization factor. So this will be ensemble of random matrices, which we will work with. Now, although ensembles studies of eigenvalues of Geneva ensemble has a long history starting from works of Geneva in mid-60s, it was not until the end of last millennium when people really got some interest and some meaningful and interesting results about eigenvectors of these matrices. In contrast to the case of classical ensembles of invariant ensembles of random matrices for self-adjoint case, where there is no, in fact, issue about statistics of eigenvectors, because eigenvectors for such invariant ensembles, for example, Gaussian unitary ensemble, they are just random set of vectors forming columns of unitary matrix, and basic which is hard distributed. So every on the group. So basically, every eigenvector is just uniformly covers unit sphere, and there is nothing interesting in, which one can ask about this type of eigenvectors. In contrast, eigenvectors of Schneeber matrices, they are meaningful, interesting, and rich objects, as we will see. The first people who studied them were in fact not mathematicians, but as frequently happens, interest arose in theoretical physics. And John Choker and Bernard Melich, motivated by some physical application, asked this question, and to a large extent set this field into motion. They understood that in many applications that it makes sense really to consider the whole matrix, which they called the matrix of eigenvector overlaps, which are just made of these scalar products of left eigenvectors and right eigenvectors. So for normal matrices, this will be just identity matrix. It will be 1 on the diagonal and 0 off diagonal because of orthonormality of eigenvectors for normal, in particular for self-adjoint matrices. But for non-self-adjoint matrices, this turns out to be a non-trivial and rich object. And in particular, diagonal entries of this matrix with I equal to j are exactly squared of these eigenvalue condition numbers that we discussed, which control stability of eigenvalues of such matrices with respect to additive perturbations. In order to provide some non-trivial but simplest characteristics of these diagonal entries or eigenvalue condition numbers, Choker and Melich suggested to consider the following object. In my lectures, I will use the following notation for taking expectation with respect to complex Schneeber ensemble. I will use these brackets. So if you see brackets, it just means averaging of Schneeber measure, complex Schneeber measure. And now the following object is of interest is just basically the moment, certain moment of this eigenvalue overlaps weighted with delta function weight. It means that we are interested when studying this object in statistics of overlaps corresponding to eigenvalues in the vicinity of position z in the complex plane for various values of z. So this delta is just Dirac delta mass at corresponding eigenvalue. In particular, if I just replaced this OII with unity, I will get the expectation of the empirical density, which is defined as sum of delta masses at corresponding lambdas. In fact, okay. Here, I noticed misprint. I will try to change it. Maybe in the notes, finally distributed, it should be lambdas are just should be z's. It just unfortunately it's these lambdas were meant to be eigenvalues of zi's. Okay. Now, Choker and Melech performed quite non-trivial computation. They use so-called, in the first of their works, they used formal perturbation theory, which was not completely rigorous, but nevertheless produced a correct result. In fact, in their second paper, they provided practically rigorous calculation for this quantity. And they found, in particular, they found the limit in that if one takes this object at, we remember that typically eigenvalues are situated within a disk of a radius square root of n, so it makes sense to write z as w times square root of n and consider w of order of unity. Then at such typical point, it turns out that there exists a finite limit of this object divided by n when n tends to infinity, and this limit is just equal to 1 over pi, 1 minus modulus squared of the normalized position of this eigenvalue, and then just chi stands for characteristic function of this condition that modulus of w is smaller than 1. It means that only this object is non-vanishing. This limit has a non-zero value only for eigenvalues inside this circle of radius square root of n. If we look at this expression, we understand that one should interpret that typically the squared condition number is of order, it should be of order of n, and therefore it's parametrically big in comparison with normal case when it's equal to 1. And one of the main goals of my lectures will be to show how to derive this Checker-Melech result in a way different from Choker and Melech, which can be also applied to evaluating some other quantities. And in order to prepare the basis for this, let us start gradually with understanding how one can address a possible way and quite efficient way of addressing properties of both eigenvalues and eigenvectors of Genibor matrices. For this, it's useful to introduce the notion of so-called partial Schur decomposition for non-normal matrices. And this is used while introducing the notion of so-called householder reflections, which are summarized in this lemma, namely taking any complex n-component vector x, one can show that there exists a unitary Hermitian matrix P. So it's simultaneously it's Hermitian, so it's equal to its Hermitian conjugate, and it's unitary, so its product with its conjugate equal to identity matrix, such that when multiplying x with such P, it transforms it up to complex proportionality factor to first basis vector, which has component 1 in the first entry and the rest 0. So this is easy to prove. Proof goes like following. Let us take our x and consider projection of its on this basis vector, and so it's basically first component of this, and basically we write it, it's complex number, so we write it in terms of its modulus and its argument. And then introduce the following vector u. It's just our given vector x. And then to it, we add a vector proportional to this basis vector. And proportionality is just the norm of our vector x, so square root of its square, with the corresponding phase defined here. And then this defines n vector u, and then we just normalize it, divide it by its norm. So we get complex vector of norm 1, and then construct matrix P as just identity matrix minus 2 times V tensored with itself, with its Hermitian conjugate. And then it's very easy to show. Precisely this such matrix P is called householder reflection, generated by vector V. And it's easy to, hermiticity is obvious. Now multiplying it with its joint, one can see that it's very easy to check that it's indeed, from its construction, it's unitary. Again, by the simple direct computation, one can find that it indeed satisfies this stated property, with K being precisely this complex number given by this phase factor and norm of original vector x. Now, why these householder reflections are useful is shown in next theorem, which basically one can call a theorem about partial Schur decomposition. Namely, suppose we have some general complex valued matrix G, and suppose we know that it has eigenvalue Z1 with corresponding to right eigenvector R1. Then one can find always two complex vectors, one of norm 1, which will be in fact used to build householder reflection, and another just general complex vector of dimension n-1, and a matrix of dimension complex valued matrix of dimension n-1 times n-1, such that our original n by n matrix is represented in the following form. It's a matrix of the following form. In its upper left corner, we have precisely this complex eigenvalue Z1. Then in the rest of the first row, we have this conjugate of this vector W. And then in the first row, in the first column, we have everywhere 0 below the first entry Z1. And then G1 is just a general block of size n-1 by n-1. And such a matrix is multiplied with from the left and from the right with one and the same householder reflection P. And P is householder reflection generated by this vector V. So how to see that this is indeed the case, that such a representation, which is exactly this partial Schur decomposition, can be found. We start with eigenproblem for the right eigenvector R1 and multiply it, now take, according to the lemma that we just discussed, there exists such householder reflection, which when multiplied from the left with our eigenvector R1, converts it to up to proportionality constant to E1, to the first basis vector. So let us take such Householder reflection and multiply our right eigenproblem with the left with such a Householder matrix. Using this property, we immediately see that we come to such an equation. And now the left-hand side can be rewritten by inserting the identity matrix, which is P times P, because P is Hermitian and unitary. So P squared is identity matrix. So we can, between G and R1, insert this identity in form of P and P. And now using that PR1 is KE1, we conclude that we have such an identity PGP acting on first basis vector is just Z, Z1 in fact, should be Z1 here. Z1 acting, just multiplying with E1. And then writing it to the components is easy to see that PGP is exactly of this form. It's just equivalence statement. Okay, so we now showed that indeed such decomposition is possible. One can always show, I mean, by simple consideration, that V can be parameterized in terms of n-1 component vector Q in the following way. It's just it's n-1 components just given by independent vector Q, and then the first component is just 1 minus Q conjugate Q, and this then will be obviously a vector of unit norm. And then, of course, we should take Q smaller than norm smaller than 1, but one can also show that by independent consideration that first component should be larger than 1 over square root of 2, and then imposes additional constraint. So in fact, norm of Q should be larger than 1/2. And then explicitly in terms of this V, just writing Householder matrix, it's written here in explicit form. And with this choice, one can show that transformation from original set of n squared complex entries of matrix G to the set of n-1 squared complex entries of G1, then n-1 complex variables in W, n-1 complex variables in Q, and 1 complex variables in 1. This is one-to-one mapping. So can be, basically one can use this set of variables as just a choice of coordinates on the manifold describing our complex, general complex matrices G. And since it's just a parameterization of new coordinates, we can we should rewrite the flat Lebesgue measure in terms of new coordinates. And of course, it will be volume element in all these new coordinates, but since it's a change of variables, obviously we will have some Jacobian, and Jacobian will be non-trivial, and one should calculate it. This is some exercise, not in one line, but one can do it. I will just sketch major steps and leave it to you to complete this exercise. But basically, the result is that this Jacobian is up to some known constant, which can be explicitly calculated, but and of course should in principle be calculated, but we won't give it explicitly. Then some factor which is explicitly written here, depending only on vectors Q and on vector Q and its conjugate. And then the most important factor, modulus of determinant, modulus of characteristic polynomial of this block, this reduced block of size n-1 by n-1 squared, modulus of this characteristic polynomial squared. So this is the Jacobian. Now, how I just sketch main steps in evaluation of this Jacobian. So we have this relation between two ways of writing the matrix G in terms of new coordinates. Then we just differentiate it to consider the matrix of differentials. And using the fact that p squared is 1, we just use PDP is equal to minus dp times p. If you want to differentiate this, is obvious. And then one writes differential of G in new coordinates in this way, extracting factors p outside, because when one basically does such a calculation, external factors which are unitary, it's easy to understand that they won't change Jacobian, can be always omitted. They won't affect our calculation. And then one just explicitly shows that PDP has the following form. It's just differential, some differentials, okay, of some complex variable here, of complex valued vector here, and here is a vector of matrix differentials. And all these entries, of course, can be explicitly calculated as functions of our variables, which we just introduced. For example, is just the simplest one is, of course, just this dA. I just give it explicitly in terms of differentials of Q, and similar, but of course, much more cumbersome expressions, explicit expressions exist also for these differentials. So for the time being, let us consider really A's, H, and F as mu variables, and then we express in terms of them, and then calculate in one more step transition from our variables.
I'm sorry, I have a question. And what does the bracket mean?
Bracket, which one? This one?
This one, yeah.
It's just no. It's just it can be. It's usual bracket. It's nothing specific. It's not commutator or something. It's just notation.
And in the previous slide.
In the previous slide, let me.
Yes.
It's the same. It's just it would be too cumbersome to use. One can use probably brackets of different size, but I prefer to use just of different type. But these are not something specific. It's just brackets to show multiplication.
Maybe ask the questions. So, okay, ask questions. Otherwise,
yes, please.
Okay. So, if you do you have some questions? No.
It's technical procedure. You see, by the way, for those who will do this exercise, I hope some people, you may start with just simplest case, probably 2 by 2. Then it's a relatively simple calculation, but it has already all necessary ingredients. But of course, it's much simpler than general case, but it will show something. Now, using this, okay, now taking this PDP and explicitly in this form, and using the substituting.
Our goal now. Wait, let's. So what we are doing now? What is our goal?
We are doing the following. We are calculating this basically how to express this matrix of differential of our original differentials in terms of new variables. Because this is the way how to one of possible ways of calculating the Jacobian of transformation. One can read.
We are doing change of variables.
Yes. Basically, it's the technical question is one changed variables from one set, one coordinates on this matrix, which is just element wise, to new coordinates. What will be the incurred Jacobian? This is the main question, technical question. And for this one, just basically needs either to use standard definition of the Jacobian, or there are some alternative ways just to read it off from Euclidean length element trace of dg times dg conjugate, and from this quadratic form read its basically metric, and then square root of modulus of determinant of this will give you volume element according
structure to this changeable.
Right, the same integral of different.
Yes, so this after the short decomposition. No.
Yes.
Yes. So we are just interested. It's just showing how to. I mean, main steps of evaluating this Jacobian. It's technical step, but it's necessary, and in fact, it's one of technically most involved steps. Okay. There are various ways of doing this. In the original paper by Edelman, from where this computation is written, he uses the so-called wedge product for doing this. It's also possible, but so there are various ways of doing this. But I just consider one of possible ways. I just take this, write these differentials in new coordinates. So we arrive to this structure. And now, if I suppose that these tilted variables, I mean, they're in fact some complicated combinations, but they are obtained by just linear shift of our original variables. So, for example, dz tilde is just dz1 minus something involved differential of h, and this dw is of similar structure, and so on. So when we see such a combination, it's one easily can explicitly write in it, calculate the corresponding Jacobian. For example, from this structure, it's clear that if we change from G to new variables, these tilted variables, the only Jacobian factor will be just modulus square of this factor, right? Because it's just change from what set of complex variables, holomorphic change to set of another complex variables by multiplying with the metric. So corresponding Jacobian is modulus of corresponding determinant. And now what remains is to calculate further change of variables from these tilted variables to the original variables. And this is calculation, which is in fact also, I mean, quite involved. I won't give it here. One can do it, and then one get this factor f. Unfortunately, in the lecture note, even on the board, it's not easy to give this computation. It's just I just sketch necessary steps, and you may try to do it again. 2x2 example is already quite informative when you do this. Okay, so why? So now we did this. Suppose that we completed this non-trivial calculation of the Jacobian. Then we are done. We are now can write the Geneva probability density. So we know that originally entries of the matrix were independent, identically distributed complex variables with respect to corresponding flat Lebesgue measure. Now we need to rewrite this in new coordinates, and this is precisely why we needed this Jacobian. So you see that elements of this Jacobian appear here as the factors and appear here. And all the rest will be just rewriting the Geneva weight, which is exponential of trace of G conjugate G, which is very easy to write explicitly in new coordinates. It will be just sum of modulus the one squared, modulus of this vector squared, squared of this vector, and then trace of the remaining part. So I write it explicitly now in new coordinates. This Geneva measure it separates, in fact, this Gaussian factor for the eigenvalue. Then again, Gaussian factor for W. So we see that, entries of this vector W, they are just standard normal variables. because basically the probability density just factorizes. This is just factorizes, separates. Then it will be some probability density on elements on Q with non-trivial factor coming from the Jacobian. But it won't have any problem for us because this can be relatively easily performed. One should remember integration domain on this Q, which I already mentioned, that Q has norm between 1 and 1/2. And then we see, that this block, lower block G1, in fact, has the following probability density. It's like it used to be for Genibor. So this block has a weight, this Gaussian weight trace of G times G conjugate. But it also weighted now with this Jacobian factor modulus square of characteristic polynomial. And this is really the main outcome. In particular, already from here, we can, from this representation, we can calculate or see what should be the way to, or could be the way to evaluate just the mean eigenvalue density, which corresponds to taking this joint probability density of all these eigenvalues and just integrating out all W's, Q's, and in principle integrating over G. So we see that basically we get the following representation, that up to a factor exponential minus Z squared, mean density coincides with expectation of modulus squared of characteristic polynomial of basically of a Genibor matrix of size n-1 by n-1. So if we develop, as we will do in the next lecture, efficient ways of evaluating this type of averaging over Genibor measure, in particular of products of characteristic polynomials, then our first result will be just to get exactly up to proportionality factor, which can be restored, in fact, from normalization easily. And it's equal 1 over pi times gamma function of n. We will get in this way.
I'm sorry.
Yes?
I'm sorry. I have a question. Is this formula is there the modulus z squared in the exponent, or there should be modulus z1 squared? No. I write.
It's okay. It should be probably z here also, because it's, you see, basically what I it's yes, it's misprint here. It should be z. Because
Okay.
I basically calculate the eigenvalue density at point z in the complex plane. For this, I just multiply this with delta weight and delta mass and average over the whole ensemble, right? By definition, this will be density of the eigenvalue, right?
Right. Thank you.
So it's just z here. It's not z1. Should be z. Okay. Okay, so it's just byproduct. It's not our main object, but we will need it later on. And it also shows at least a possible way of relating the eigenvalue density to characteristic polynomial, which is interesting in itself. And we will see that, in fact, that also quantities related to eigenvectors can be expressed as some more complicated averages of products of characteristic polynomial, basically. Okay. Now, what about eigenvector overlaps, which are our main object of interest? How to read them off from this representation? First of all, in this partial Schur decomposition, we immediately see that right and left eigenvectors of this block or this matrix R basically obtained from original right and left eigenvectors just by rotation by P, obviously. And since P squared is 1, it means that our main object of interest, this matrix of left-right overlaps, it remains invariant. So it's enough to consider left and right eigenvectors of this matrix. Okay. The right eigenvector why this form is nice? Because right eigenvector is trivial. Right eigenvector is just first basis vector, as it's obvious from this form. Left vector then can be written, left eigenvector corresponding to Z1 can be then by Bayer-Than normality must have the following form. It should be first component should be 1, and then should be some vector, which we now take this matrix and write its left eigen problem for it. And then after very simple algebra, just multiplying this vector with such a matrix, we immediately can solve for this unknown vector B, which is main non-trivial component of our left eigenvector. And we just see that it's nothing else as this W, conjugate W times a resolvent matrix for G1. Resolvent matrix at value spectral parameter equal to the first eigenvalue. And this is well defined because basically also this form is nice because we see that one can first of all iterate this procedure and then perform further Householder reflection or this partial Schur decomposition, make it further and find Z2 as the first eigenvalue of G1 and so on and so forth. In this way, one can fully find all eigenvalues, but we are not interested in that. We are now interested only in the first eigenvalue and corresponding eigenvectors. So we see since all eigenvalues of G1 one can show, I mentioned that they are eigenvalues other than Z1 of the original matrix, and since all eigenvalues are non-degenerate, this is well-defined object. So one can invert it. And then one can immediately, from knowledge of right and left eigenvectors, just to build our favorite object O11, which is squared condition number corresponding to the first eigenvalue. And taking this form, we just immediately see that it can be written as in terms of the following matrix is just the matrix product of two characteristic matrices for G1 and its Hermitian conjugate. So this matrix B is Hermitian matrix, a positive definite Hermitian matrix, non-negative, in fact, and can be no, it's just positive, even positive. So it can be, it's invertible. It can be inverted, and its inverse is sandwiched between W, and this is the main object which determines difference between O11 and 1. And now we remember that 1 is the value which this condition number or diagonal entry of overlap matrix would have for normal matrices. So this object is exactly what we are interested in. It's a deviation from normality is controlled by this. And we will be interested in finding, in principle, one can find the whole distribution of this random variable. But we will be interested now in computing just its first non-trivial moment, just expected value. First, it's very easy to average over, to perform averaging over W's, since W's I showed to you, they are just Gaussian normal standard variables. So it's trivial to perform this averaging of quadratic form in Gaussian variables. And the result is that one gets just after averaging, one gets trace of this matrix. So basically now one needs to find a way to evaluate trace of inverse of this matrix B. Okay. Now, but now one should basically remember that one needs to build this object, so-called Choker-Metek correlator. One should take this O11, weight with it's with corresponding Dirac delta mass centered at eigenvalue Z1, and then average over the ensemble. So if we do this, nothing depends on these variables Q's. So integration over them will give some constant, which later on can be fixed from, say, normalization. So these Q's won't enter this computation. But, of course, the part of Jacobian given by this modulo squared characteristic polynomial, it's there. So our goal now is to perform this average, which looks quite non-trivial. One should it has two terms. First term is basically nothing else. We already know this will be just a density, because it's just modulo squared determinant times exponential minus z squared. So this is exactly the density. So density is a part of this computation. But even less trivial is to take the ensemble average of this trace of inverse B weighted with this characteristic polynomial. Now, noticing that determinant of the matrix B, this was the matrix B defined, its determinant is just modulus, exactly modulus this factor, modulus square of characteristic polynomial. We then can rewrite this expected value only in terms of matrix B, and this is just this expression. And then the trick is to notice that if one introduces an auxiliary matrix of the following form, it's block matrix of size 2n by 2n, and its determinant, if we use the standard ways of standard method of evaluating determinants of matrices decomposed into blocks, and using the fact that we have on diagonal, we just introduce basically auxiliary parameter mu, which is just positive parameter mu. And on diagonal, we have square root of mu times identity matrix. And off diagonal, we have up to factors I, we have this product, these matrices n by n, which are characteristic matrices for G1. Then it's easy to check the determinant of this matrix M, which depends on two parameters, on Z and on mu, is just equal to determinant of mu times identity matrix plus our matrix B. So taking derivative over mu, we just reproduce this. When one takes derivative of determinant, one always get trace of inverse matrix. So setting then mu to 0, one exactly get this combination. This trick is, and this generalization is very helpful because it's now reduces computation to evaluating determinant of a matrix M, where G1 is a Genebra matrix of size n-1 by n-1. So all entries are independent, identically distributed complex numbers. And this, of course, has advantage because to perform such average, we will develop a very efficient procedure to average of such matrix B, where G enters quadratically without this trick is much more problematic. So basically, in the next lecture, I'm going to discuss the method, which is I know that already you had an exposure, or maybe we'll have tomorrow, I'm not sure, to integration of anti-commuting Grassmann variables. This will be the method which allows to compute averages of this type very efficiently, namely determinant of matrix M of this block matrix will be expressed in terms of integral over Grassmann variables, Gaussian integral over Grassmann variables, where in exponential we will have quadratic forms in Grassmann variables built on these blocks of matrix G1, and then using Gaussianity of G we can perform in a very simple way, in straightforward way, ensemble average over ensemble of G1, and in this way the problem will amount to performing analysis of some integral, which we will see how to do it explicitly for any n, and eventually how to perform its limit to evaluate its asymptotics when size of the matrix is big. It will be done by some steepest descent or Laplace or variant of Laplace method. But this I will give all account of this procedure. I plan to give tomorrow in the second lecture. Thank you for your attention, and please ask questions in the remaining time.
Thank you very much.